But let's start with some basic definitions of special relativity. First of all, we are going to be working with objects at constant speed, but their speeds are going to be very, very, very fast. Things with relativistic speeds are roughly 1/10 of the speed of light, or as we say, 0.1 c. Anything less than that, even though it may begin to have what we call relativistic implications, we're going to ignore it below that. Most of what we're going to work with will be above 0.2 c, etc. If you imagine two objects moving relative to one another, that would be like, we are here on the Earth, and an object goes past me. Well, we have this idea that because the Earth is fixed, that object moving past me, that we're at rest, it's moving. But what about us and Venus? Venus is roughly the same size as the Earth. That's why I picked Venus. So if we're both moving around the Earth, Venus takes less time. But let's just say at some point we're getting close to each other. Who's at rest? People on Venus would say they're at rest and the Earth is moving. People on the Earth would say we're at rest, they're moving. Which one's right? They're both right. The number one thing in special relativity you must constantly remind yourself is there is no one absolute reference frame. They are all equally good. Okay? Now, when we say that, that would be, for instance, I'm right now on the Earth's reference frame. That an object moves in front of me, I'll say it's moving this fast with relative to the Earth. When I say relative to the Earth is 0. But what if it's a train, and I'm on the train, and I see an object going by that's stuck to the Earth, say a tree, right? I'm on my train reading my newspaper, oh, a tree goes by. I could say that tree has a negative velocity relative to me. Now, its velocity relative to me is the opposite of my velocity relative to the tree. Now, how we're going to write that, just to get used to this, is we're going to say the velocity of object 1 relative to object 2. Now, let's say that that's 6 meters per second. Okay? The velocity of 2 relative to 1 would be -6 meters per second. Simple enough, yes? But we do have to get used to this notation, 1 relative to 2. And that could be a rocket relative to the Earth. It could be the Earth relative to the rocket. Okay? Other things that we must do. Let's start off by talking about our basic definitions, and we're going to use real-world stuff of non-relativistic, in other words, our everyday life, to build our vocabulary for special relativity, and it turns out this will work. So, let's start off with time. If we, in our everyday life, have a stopwatch, I pull out well, nowadays it would be my smartphone, but I pull out my stopwatch, and something happens, and I see a car goes, there's like a place here and a place there. How long did it take to go a quarter mile? If I'm far enough back, I go, and I can just go, oh, look, it took that long. And notice I use one stopwatch to tell the amount of time. One stopwatch. So for time, the proper time, it's written different ways, but we're going to use this one. The not stands for proper. Why they use not, I have no idea. It's just what John Coley uses. I'm pretty sure. Either Tipler uses that or he uses a tau or something. We can work through that. 1 clock. Okay? We're all good on that? You only need 1 clock to properly tell the time for that object. But what about length? For length. You know, you've got that distance, right? Well, in order for me to measure that distance, or to measure a distance of this table, well, I need 2 positions. I can't measure it from here. I need this position and this position. I need 2 positions, yes? L naught or L naught, I'm not sure which one, is 2 positions. Okay, that all seems pretty obvious, yes? Now again, you might think that this is very silly. It will not be. Okay? Number 3, mass. If I have an object, and the example that I used on my worksheet was, what about your dog? I need my dog, I need to measure the mass of my dog. How heavy is my dog? Well, the first thing I got to get the dog to do is
Sit.
Sit in one position. So, when you are measuring proper mass, and is that still an M naught? I didn't actually give that one. Okay, so the proper mass is at rest. Okay? Those are our three basic definitions. Proper time, proper length, and proper mass. Proper mass must be at rest. Proper length must be measured with 2 positions. Proper time measured with 1 clock. Now, what about objects that are moving very fast? Well, if we're here on the Earth, and we're here, let's say we've got our, let's just imagine we could see things happening. And let's just say that the object is moving very fast, relativistic speeds, meaning close to the speed of light, and it's bright enough that we can see it moving. So it's made shiny enough, or let's just say it's got a beacon or something that's moving, right? We can see that beacon. And so let's imagine this spaceship zooms by us and then gets to Saturn. And it goes from here to there. Well, let's look at the proper time. Well, first of all, as this object passes here, we go, ready, click, and it passes us. And as we're watching it, we're like, click, it went by Saturn. And you might say, well, that was 1 clock. The problem is, doesn't it take time for this light to get back to the Earth? So by the time I go, click, that object is past Saturn. My time is wrong. So, we're going to fix it this way. Let's imagine that every reference frame has a system of clocks and meter sticks. Think about it like this. They go infinitely in all directions. So think about this expanding in all directions. We're mostly going to work in 1 dimension because, good Lord, it would be terrible in 2 dimensions. But let's say this is the Murray reference frame. And as I'm moving like this, my clocks and my meter sticks go with me. And those clocks and meter sticks are massless. Otherwise, it gets weird. So let's imagine this is the Earth's frame. I'm just going to put that there. Okay? Please stay. There we go. So that's the Earth's frame of reference. This is the Murray frame of reference. Mine's moving with me. That one stays stuck to the Earth. You are all in the Earth frame of reference. You're not in the Murray frame of reference because you're not moving. So imagine, in this example, the Earth has meter sticks and clocks that go everywhere in the universe. And so does the spaceship. The spaceship is moving with its own clocks and meter sticks. We're good? I would need a clock here, and there's another clock here, isn't there? Remember, they go throughout the entire universe. And then when it passes me, the clock here goes click! And then as it's zooming by, as soon as it gets to Venus, there's a photo gate there that goes click! But notice, I needed 2 clocks to do it. Not the proper time. But the guy in the spaceship, who has his clocks moving with him, there's a clock right in the center of the spaceship. He goes click when he passes the Earth and click as he passes Saturn. He only needed 1 clock to take that time. The proper time would be for the spaceship. Turns out that these times are different. The time that I read and the time that he reads are 2 different times. And they will not agree. But you might say, but he's moving. Relative to me, relative to him, I'm moving the opposite way with the same speed. But my clock is right. To you it is. But to him, his clock is right. Or her clock, whatever. Their clock, if it's a space alien. Maybe they don't have gender. Okay. But what about the distance? Right? Or if you're going to break down the walls and go all the way.
Just kind of like run a few steps off.
So, anywho, so what about the length? Remember, in our world, if we want to take the length, we have to have 2 positions. Well, who needs 2 positions here? You see how he can go from here, so it can go from there to there. 1 position. 1 clock. We need 2 positions, don't we? We read the proper length.
But aren't the Earth and Saturn still moving between the time that he passes one planet?
Let's do one thing at a time. Let's just try to make it easy. Okay? Now what about, hold on to this. What about the length of the ship? Do I need 1 clock or 2 clocks to measure the ship?
I think you need 8 clocks to
I'm saying one position or two positions. When we say clocks, remember that there's, what we need to imagine is that everywhere in the universe is meter sticks attached to clocks. Now again, because you might say, but what if we're talking about really small distances, which we will in one case. But because most of what we're talking about in this chapter are going to be huge galactic, so cool to say, galactic distances, right? That a meter is close enough. You know, between here and Saturn, if we're only off by a couple of meters, we did very well. Okay, so at the end of each meter stick, imagine there's a clock. So when you see this, imagine that there's meter sticks combining all of them throughout the universe. So when I say how many clocks, I'm saying at the end of each meter stick is a clock. How many clocks do I need to measure his length? Well, if this is the ship passing me by, I'm right here. I can take his measurement here and his measurement here. I'm in the same position, aren't I? I only need one position to measure. Because if I know his speed and I know the time, I know his length.
But the alien needs two, right?
But the alien would need to get out of his chair, cruise control, and measure the other end of the spaceship. He needs two positions, or it needs two positions to measure the spaceship. I could do it by just staying in one position, going, there was the front, there was the back, I know how fast he's going, there's his length. And by the way, the length that he measures, or it measures, we'll go there, and the length that I'm measuring are not the same length for the ship. We get different numbers. Likewise, the time for the spaceship to get between here and a distance very far away at relativistic speeds will read differently between me and them. They get a different time than I do. And I won't tell you what that is yet. We'll get there in January. Because if we can get this down, this opens up all sorts of possibilities, okay? Now what about mass? How do I measure my dog when the dog is?
Sitting.
Sitting. So for me, is the spaceship sitting? Is the spaceship at rest?
No.
I do not read the proper mass. Turns out he reads, if he's fast, he reads heavy to me. That spaceship is heavier than it is when it's at rest. But for the alien, the spaceship is at rest. The alien measures the proper mass.
Yeah, you're definitely going to need to shorten this video.
We're going to do this a few more times, aren't we? So once again, in your real world, yes.
So the proper length is measured by the alien
Why?
because there's two positions.
Two positions. How would I measure?
So it's
How
the
would I
alien
measure the length? Because how would I measure the length of that ship? All I would need to know is the time between the front and the back of the ship. Yes. And if I know this, and we're going to say in this case, I know the speed of the ship. And by the way, the ship knows my speed because the ship believes it's at rest and I'm moving backwards. Remember, whose reference frame is better? They're all equally good.
Mine.
Yeah, everyone thinks that mine is better. If you're the alien, you're right. But for me, I'm right. Okay? Do we follow? So proper length, you need two measurements, or we'll say 2 clocks. For proper time, you need one clock. And for mass?
At rest.
Okay, that's all we need for today.
So the alien is all three.
The alien
No.
measures all three.
No. Ooh, let's back up. The alien is not the same for all three. The alien is not correct. The alien reads the proper time, but not the proper length. Because isn't it the same clock for them, the clock in their hand, when they pass one and they pass the other, for Saturn and the Earth?
I was thinking about length of the ship.
Length of the ship, let's do that.
Oh, okay.
Let's do that. For the
Got
length
it.
of the ship, yes, the alien measures the length and mass of the ship correctly. But what about the distance to Saturn and the trip to Saturn? Who measures the proper length to Saturn? We do. Who measures the proper time to Saturn?
It does.
The alien does.
Sorry, I think we were both talking about the length of the ship.
Doesn't matter, as long as, but you see what different things though, and for the ship, yes.
Yeah.
But there is no proper time for the ship because according to him, the ship's not moving.
Yeah, I don't know why we were thinking that.
That's fine.
Yeah.
No, that's fine, but notice it gave us 2 different things to think about. Okay, how do we feel about that? Pretty good?
Yeah.
All right, we'll do more of that in January.